Hey, good morning. So this week I'm going to cover two chapters actually, chapters 6 and 7. In the previous edition of the book, they were in the same chapter, but this edition they decided to split into two. Not clear if that's actually better, but still, I think that's enough for the content of 1 week. So this week is all about synchronization tools or synchronization mechanism, so to speak. Give you a background, and critical section is this key concept, and then to do synchronization, really what you need to do are either semaphores or monitors. And actually the classical problem of synchronization, that's the topic for the next chapter, but we'll see a little bit of this chapter too. And so really the key part is going to be semaphores, and that is a fundamental construct. It's rather low level, but you'll get to implement semaphores in your checkpoint number 3. And you'll get a good idea of what it is. And you really need to pay attention to semaphore because it can be used in many different ways, very flexible, very expressive, but then it's very low level, so you got to know what you're doing. Okay, so why do you need synchronization? Well, because you have things that are running concurrently, especially when they can get preempted, or you have multi-threaded execution and they're sharing data. And so you need some mechanisms to ensure that they, in certain parts at least, they follow a certain order, or else bad things can happen. So let's go back to the producer-consumer or consumer-producer problem. Previously, we only had one version where it was only for a producer and a single consumer. And producer would only update one of the pointers, so to speak, and consumer only updates the other, right? Remember? And so one of them was an in pointer, one was an out. So the producer would update the in, right? Because it's sticking data into the buffer. So that's why you see here, producer in gets in plus 1 modulo buff size, whereas consumer only updates out because that's where it's pulling out. Once it pulls out, you have to increment the out or wraps it around, right? So because only one process updates one variable, and that kind of sharing is okay because you don't have the chance where two processes update the same variable at the same time. But let's change this problem so that this is following the book, so let's add a count. Because the previous one, you actually, in the case of full, it's not really full. There's one empty buffer that's not used so that you can test if they're equal, in equals out, then you consider that to be empty. Whereas if you really want to utilize that, you can't tell empty apart from full, right? So, but if you add a count, well, guess what? You can actually utilize that extra buffer space, right? Now, the difference here, though, is the count is now read and updated by both processes. Because if I want to enqueue an item, I increment the count. If I want to dequeue, I decrement the count, right? So unlike the previous case where in was only changed by producer, out was changed only by consumer, now you have a count that's looked at and changed by both, right? And you can have a problem. Count plus plus, count minus minus. Say, really? I mean, it looks like a single instruction to me, right? Count, I increment, I decrement. This is a single statement. Well, it's a single statement in C, but it can be multiple instructions in assembly. So let's go back to assembly, our favorite level of looking at things. So in CISC instruction, yes, indeed, an increment or a decrement could be a single instruction. In fact, inventor of C language, he decided to include the plus plus operator. Why? Because they initially targeted PDP 11, and it did have the inc instruction. You can inc, so increment, either a register, a memory location, an indirect, whichever. Right? So it's very flexible. But of course, That was for a CISC instruction set. As you know from computer architecture, CISC is complex instruction set architecture. It's great for the programmer. It's a lot of fun to program, but it's a lot of work for the computer. So it makes it difficult to pipeline, difficult to handle variable length instructions, very complex to design the hardware, just so that programmers have an easier time coding assembly. 8051 happens to be a CISC instruction set architecture as well. So it does have an INC. It doesn't necessarily have a DEC for decrement, but VAX at least does. And INC, as you can see from the instruction set documentation, it works on registers, works on direct, works on a number of different addressing modes. So in those cases, fine, no problem. It is done in a single instruction, and as you know, context switch cannot happen in the middle of an instruction. It happens only on instruction boundaries. So an interrupt comes in. If you haven't finished an instruction, pipeline gets flushed, right? It empties the pipeline. Once it hits the instruction boundary, then interrupt comes in. However, even for CISC instruction set, depending on the data type, like 8051 is an 8-bit architecture. All registers are 8 bits. What if you declare your variable to be 16 bits? Well, guess what? It has to emulate the 16-bit operation using a sequence of 8-bit instructions, right? Including taking the carry, including adding it a carry, and so forth. Well, with RISC architecture, a little increment like that turns into 4 or 5 instructions. And so what does it do? Well, this is an example taken from the MIPS architecture. Some of you may have had it, but let me explain that to you. So LA is actually a it's a low address instruction, kind of like move A, right, to DPTR on 8051. So it loads the address and then into a register. But really, it's not the full address. It's only a part of the address. And then you need to, so it actually does 2 parts. To load a 32-bit address, you actually load 16-bit at a time and or in the other 16-bit, the upper and lower. So I say, well, really? Yes. In RISC architecture, they really the code density is much lower. They take many more instructions, but a fixed width, lots of registers, but then take more instructions. Why? Because it makes this machine simpler. You give the work to the compiler. They didn't think people would want to code in assembly anymore. So a compiler generates a sequence of instructions, very easy to pipeline. And in the end, you save power. You can pipeline it very well, high performance, low power, everything. So LA actually is a pseudo instruction in that it gets expanded into 2 instructions. That's called LUI and ORI. So load upper immediate, so that's 16 bits, and into the upper 2 bytes. And ORI is to OR in the immediate into the lower bytes. And then that way that forms the address. Once you have the address in register 4, in our MIPS notation is all $sign as opposed to R. Then you do the dereference of register 4, which has the address, load it into register 10. Okay, so that's essentially R4 or $4, that's the pointer. You load from that address into register 10. Okay, so that's just to bring in the count. Then what do? You add immediate. You add 1 to it. And in MIPS notation, they don't do pound sign. 1 is 1. Okay, so add immediate. So register 10 gets register 10 plus the constant 1. That's what ADDI does. Then you have it still in register. You got to store it back to the memory. So SW, store word, using the address or pointer already in R4, register 4. What value? Well, register value in register 10's value. Okay. So a simple increment gets turned into, well, looks like 4 instructions, but because the first one is really a pseudo instruction, so there's really 5 machine instructions. And each one is 4 bytes, so it takes 20 bytes of instruction to do an increment. Okay? Compared to little 8051, if you do inc A, that's a single byte. Inc R0, that's probably a byte or 2 bytes at most, or if you do a direct one, that's probably 2 bytes, right? So much more economical. So the code size on the MIPS is way bigger, but they get the benefit of much simpler architecture, much more streamlined, pipelinable, but that's a price you pay. So what does that mean? That means, well, you got now 5 instructions. There are 5 instruction boundaries where interrupts could come in now, as opposed to a single instruction where it's only before and after. So a C statement can translate into 5 instructions as shown here. And so do you really want interrupts to come in anywhere in the middle? That wouldn't be a good idea, would it? So let's take a look. So where could context switch happen? Ideally, you say, well, before my count plus plus or after my count plus, not in the middle of it. So, okay, ideally, yeah, share count is 5. Load in 5, add, and that's still in the register, save it to share count memory. Great, nothing bad happens. The other, well, the context switch happens. The other one wants to decrement. Great, it already sees an updated value of 6. Loads it into memory to the sub I, which decrements it. 5, writes it back. Great, no problem here. That's an ideal case, right? Interrupt does not happen inside an increment or decrement. But can interrupt happen in the middle of a decrement or increment? Yes, in the case of MIPS. So let's see, we do, instead of those, well, let's just say 4 pseudo instructions. So LA, let's just consider that to be 1. But theoretically, it could happen in the middle of LA as well. So you've done 3. Before you had a chance to store that updated count from register to memory, guess what? Context switch happens. Switches from producer to consumer. And so producer thinks, well, I wanted to increment because I just produced something. It was 5 before. I loaded 5 in, from memory into a register. I updated already in the register. I haven't written it back, right? And then now, oops, consumer takes control. Consumer, what does the consumer see? Does the consumer see 6? No, it doesn't, because each process or each thread has its own register set. So whatever the consumer sees was its save state version of the register value, right? Because there was a restore state in order for the consumer to run. Remember that? Right? So then whatever value consumer had in its register, that was what got restored. So yes, the value of the producer's register 10, which now has the value of 6, that gets saved before the context switch. Now you start running consumer, even though it's using the same physical register, logically it's a different set, right? Then when it, whatever value it has really doesn't matter. And then so what it does is, say it loads from memory. So then the share count now is still the old value of 5, gets loaded into the register, overwrites consumer's register 10, assuming it's using that. It might not be using register 10, depending on how the compiler generates code. But anyway, assuming it is, now it's 5, and does a decrement, becomes 4, and then it stores the 4 into memory. Okay? Then the consumer thinks it's doing the right thing. Yeah, I mean, I loaded from memory, nobody interrupted me, I put it back, now it's 4. And then context switches back to producer. Guess what? The producer didn't know it got interrupted, right? So all the registers got put back. Okay, it looks at my register, still has value 6. And then next step is to store this value to memory. It still had a 6. And when it writes to memory, it writes a 6. So what happened? Well, consumer's decrement got overwritten. See? So that means the consumer thought it correctly. Yes, it did. It actually wrote back into memory. It thought it was correct, but then the producer didn't know. And so by the time producer writes it back, it's just executing that sequence of instructions. It overrode the consumer's value. So now you have something inconsistent. Because what? The correct value should be what? It's definitely not 6. It's not 4 either. It's supposed to be 5, right? Because I just produced something, the consumer just consumed something. It was 5 before, increment, decrement, supposed to be back to 5, right? It doesn't matter if you decrement first, increment next, or increment first, decrement. Then this value is stuck. It's 6 from that point on. So if you rely on count to be your primary variable to decide whether it's empty or full, well, this is going to show one extra item than you really have. And so the later consumer says, one more item, I'm going to grab it. And it's going to grab junk. Okay, and bad things can happen here. So this is just one example. Of course, you can imagine different ways of interleaving the code to really mess things up. This is because there's no synchronization in the two updates to the shared variable. And this kind of thing is called a race condition. It's very hard to reproduce. You run it once, who knows when it's going to context switch. Say, oh, bug. Okay, next time you try to run it again. Hey, it works fine. What happened? Right? So you scratch your head. It's unclear. So this kind of thing, very hard to debug. So you got to really pay attention, right? And so final result depends on which process finishes last. Okay. Now, to run this on a uniprocessor or single-threaded processor, what's the solution? Well, just don't make context switch happen before and after, right? During that time. So you can disable it temporarily, do the increment, decrement, re-enable. Okay, so that's one way to disable context switch. This works as long as your section is not too long. Otherwise, you can drop interrupts. And non-preemptive or cooperative threads don't have to worry about this problem because you don't do a yield in the middle of a count. You can't possibly even write it in the first place, right? So it's a separate statement. So the language itself imposes that restriction. Now, but in general, you want preemptive threading because that's one way to protect process from some process that hogs the CPU. So that's why there's this concept of what's called critical section that should be supported. So what's a critical section? Well, the critical section problem is one where you want what's called a protocol or agreement among processes that share a variable, but you can't really do much with the variable itself. So what you can do is to say a section of code that accesses the shared variable. Okay, and so if you have a set of processes P0 through Pn-1 that are trying to access a shared variable or some shared data, the critical section is one where the different processes will do what's called mutual exclusion. So they exclude each other from entering the critical section at the same time. So in other words, at most, one process can be inside that critical section doing the update. Okay, if you can do guarantee that kind of property, then your updates are consistent. Okay, and of course, turning off interrupt on the uniprocessor is certainly one way to achieve it. There are other ways to achieve it because if you just do that all the time on larger data structure, it's actually not going to work very well. It's for one, unnecessarily restrictive. For now, the other, it actually does bad things to the performance. So the critical section has this general structure. Well, I mean, not that all processes are like that, but you can imagine a process is somewhat just repeating itself. Okay, it doesn't exactly look like that, but you have what's called section entries, the critical section, section exit, and remainder. Of course, there's other code too, but so you just this is really just show that there's code before and after the critical section. And so the three requirements, this is important. One, mutual exclusion. So that means at most one process can be in that critical section at a time. So by being in there, it excludes other processes from entering the critical section. Okay. Second is actually progress, because once you enter the critical section, you want to make sure it gets out somehow, so that the other processes that want to enter the critical section can eventually. And so that means it shouldn't be blocked indefinitely inside the critical section. Also, what's called bounded wait. In other words, not just that you can get out, but you have to get out in a finite amount of time, okay? Or actually bounded amount of time. And so the bound must exist on the number of times that other processes are allowed to enter a critical section after a process made request to enter its critical section. So so how do you actually ensure this happens? Well, that's something you can test and reason with. And as long as you can show these three properties, then yes, you have properly implemented a critical section. And a lot of it has to do with what you put in on the entry and exit part surrounding the critical section. So there are various solutions proposed, software solutions, synchronization, hardware, but that really means instruction set support, semaphore and monitor. Now, software section does not really assume that you have additional things like these atomic instructions or other instruction set support. It just uses regular instructions. And but of course, its applicability is more limited, makes certain stricter assumptions. It's probably not going to work very well on today's multi-threaded, hardware-threaded architectures. Synchronization hardware would say, you rely on certain hardware support, specifically instruction set level, to help implement the primitives for synchronization. Semaphore is the most important one in that it's very simple primitives, but then very powerful. You could use them for many, many things. Monitor is more of language level packaging. And you could certainly implement monitor. So if you think of it as object-oriented, and if you've ever done Java, synchronized methods, synchronized objects, those are kind of various forms of monitor. But then there's different variations of monitor depending on who gets to block, who gets to continue. Okay, in Java, there's it differently from other languages, from the textbook, from Python. But monitor is certainly supported in many modern languages. But still, I think you've got to know semaphore very well, because monitors underneath is mostly implemented using semaphores anyway. Okay? So first, software solution. This is not semaphore. This is just a way to use software to ensure no race condition. Well, for one, you can do a non-preemptive type of scheduling. So there, no race condition, but that's not very interesting. And you'll also have the problem of some process hogging the CPU. So assumption is you have preemptive, and there are several solutions proposed, and one of them talked about in the book, and you probably get this on various entrance exams, is this Peterson's solution for two processes. But this is really more for theoretical interest than for anything else. I mean, it could be for very simple cases, very simple architecture, but for modern processes, it's really not used as much. Okay, so what is it? Well, so it looks like this. There's two processes, okay, and they share some variables. So basically, you want code before and after the critical section to implement the critical section with those three properties, right? So what you got to reason with is really how can those three properties be shown. So what it does is it actually has two shared variables in addition to whatever you are doing. So those you can say are control variables. One is called turn, the other called flag. Flag is a Boolean array, okay, and turn indicates which process is turn it is. And so it looks like this. So they're more or less symmetric, and you can certainly write it in terms of I. That's what the book does. But here I just expanded 0 and 1 into the I. So first, before entering critical section, you set flag of yourself. So flag sub 0 for P0, flag sub 1 for P1 to true. Okay, and that is one control variable. The other is turn, but then you set it to the other process. So I'm P0, I set turn to 1. If I'm P1, I set turn to 0. Then you enter a loop. This is a while loop that checks while flag of the other guy, flag sub 1, is true, and, that's a logical and, turn equals 1. So what does that mean? Flag sub 1 is set to true by process P1. So each process upon the entry, okay, just before critical section, sets its own flag to true, right? So by setting it to true, that says, hey, I raised my flag and I am gonna enter, okay? But where I am, not sure. But turn just says, well, I want to be nice, so here. Yes, even though I'm requesting, I still let you, the other guy, proceed, right? So while tests both, and then test flag sub 1 and turn equal to 1, right? So if flag sub 1 is true and turn equals 1 true, that means what? That means P1 is currently doing its critical section, right? And then once it finishes, P1 sets its own flag to false. So, and then that's what breaks the while loop for P0, right? And same thing, so this whole thing is mirror imaged, right? So if P1 is out, then what happens? Then P0 can proceed. It drops through, right? So it enters its critical section, and when P0 is done, sets its own flag sub 0 to false. Okay, so that's a simple mechanism using two control variables to achieve the effect of a critical section. Okay. It allows context switch anywhere, anytime, okay? And so that's what it looks like. So does it achieve mutual exclusion? Yes, it does. Because I mean, it could be the case where flag 0 and flag 1 both equal to true. That just says both processes want to enter the critical section, okay? And maybe already in critical section, but whoever has the turn will actually proceed and enter. So because you only have one value at a time, right? Turn can only be 0 or 1, can't be both. That means that condition, right? The and. So first part can be true, but the whole thing won't be true until turn part. The turn comparison is true. So so it's relying on turn's value to decide who gets to proceed, right? So mutual exclusion, yes. What about bounded wait? Well, assuming the critical section itself is bounded time, right? So flag executes, always sets its own flag to false. So as long as the critical section and remainder has bounded execution time, then yes, flag will, each process sets its own flag to false, which then allows the other guy's while loop to go through, right? Because as soon as the left-hand side becomes false, while drops out. That's the way while works, right? So yes, bounded wait. What about progress? Well, while loop condition for I will always have an and condition, and it's always broken by the other guy. So because of bounded wait, one guy falls through, the other guy, bounded amount of time, gets to enter its critical section. Okay, so that's the kind of the sketch of the proof. Now, what about its issues? So it's a software-only solution. Well, yes, so that's kind of nice. Does not require hardware support, but it's not guaranteed to work on modern CPUs, especially, well, for two considerations. One, even if it's not multi-hardware threaded CPU, compilers try to do clever things. What? would that be? Well, instruction reordering, right? So if you have ever taken compilers, optimizing compilers, you know compilers basically does the CDFG or control data flow graph, basic blocks, and then it checks when it does the operation, what depends on it, right? There's a graph. And if it sees there's no dependency, it says, well, I can probably reorder this, right? Of course, compiler does this assuming that there's no shared memory, right? It's assuming it has full control over the entire variables and everything. And so it does it depending. Why would it do that? Well, so for pipeline processor, maybe it's helpful for it to schedule an instruction so it can fill a bubble, right? So that way it executes faster. Also, there may be register pressure, read after write hazard, but if you reschedule it, well, again, that's due to pipeline considerations. So compilers can do these instruction reordering, but then that messes up your ordering of setting the values, right? Because you set the values not for yourself to look at, it's for the other process to look at, right? But the compiler wouldn't know that. And of course, if a CPU has multiple hardware threads, then that's what can break it too, because then these can see value not in the same code order, right? So really, this is okay for for your theoretical interest for proving certain things, but then in practice, this is not used as much. So in practice, pretty much all processors support some kind of instruction for synchronization. And surprisingly, even the little 8051 does too, okay? So if an 8051 can support synchronization or atomic instructions, there's no excuse for any other processor not to support this, right? It's one of those such basic things that there's no excuse not to include it. So anyway, this support is not limited to instruction set, but mostly in instruction set. There's something called memory barriers. And what is it? Well, it's actually, on a lot of processes, it's actually an instruction or an operation where you want to make sure the memory has been flushed so that the value in memory is in code order, so the way you write it in your program, okay? So that requires you to actually get feedback from the memory subsystem and to know that, these memory write can take a long time. And so it's written now, not just in progress, it actually it gets committed, right? It takes effect. Of course, memory barriers can take a long time, and now in hardware instructions, mostly in the form of atomic instructions. Okay, atomic instruction is where it's one single instruction, but by the definition, interrupts cannot come in the middle of it. Can only come before or after, but not in the middle. But it does a couple things combined in one package. And that actually can help you make just the right primitives to help you build these higher level synchronization primitives. Atomic variables, I don't know if that's, book says it's under the category of hardware support, but this is more, arguably programming language level support, where variable updates are atomic. But then they say, well, you could have limited operations. So maybe it only does the update in the form of increment, decrement, simple assignment, but not anything more than that, okay? Not like an add or with a general value. But anyway, so that's the book lists atomic variables under hardware support for synchronization as well. So let's take a look at some of these. So for locking is kind of the basic thing. So locking just is a way to achieve mutual exclusion. If I lock it, nobody else gets to use it because they try to access it, they have to check the lock. Oops, it's locked. They just have to wait, right? So locking is another way of saying mutual exclusion. And on uniprocessor, you can simply disable interrupt in the critical section and then re-enable after you exit. A multiprocessor disabling interrupt can be infeasible or too inefficient. And that is true because it actually does require additional signaling and go to other ones, and they may in the middle of executing certain things, and usually flushing a pipeline can take a long time. On modern machines, what's mostly done are either atomic test and set, or more generally, atomic, what's called compare and swap. So that's more of a general form of atomic test and set. So what's atomic test and set? Well, here it's shown in like a C-like pseudocode, but you should keep in mind that somewhere down the line, there is actually a single instruction, machine instruction. That's personal, atomic, in that it's actually doing this. This is more of a calling interface. Okay, so so conceptually you see this as executing atomically. What does it do? So test and set, atomic test and set. Basically, you pass a reference to the lock. In case you don't remember C syntax, you can. This is more modern, not the traditional C. Traditional C only has a pointer. This is more influenced by C++. You pass a reference to it, so you don't have to put the ampersand address of, right? So you pass a lock to it, and then it's a Boolean variable. And then what you do is you save the current state of the lock, but only one caller can enter this function at a time, right? That's by definition of being atomic. How it achieves it? Well, that's up to, because it's implemented as a single instruction. But okay, well, you just assume that this whole thing is atomic, so only one enters at a time. And so whoever enters this sets the lock to true, no matter what. The lock could be true in the first place. So if you set lock to true, doesn't do anything. But then you return the previous value of it, okay? So now what do? So if you get a false value, what does that mean? That means, yes, I got the lock, right? Because by the time I enter, it was unlocked, which is false. And that was the old value that got returned to me. But if I keep calling this function, it keeps returning true, lock. Okay, just keep spinning, polling, or waiting, go on a wait list, right? So what you can do is you do a while, test and set, and then pass the lock to it. And if it jumps out of the while loop, that means I got the lock. I can go ahead and execute, okay? So that's, and lock is that shared variable. And so at most one process at a time should get the lock, and so it does achieve that. But this is a protocol, so that means everybody better follow the rules. What's the rule? Well, everybody calls the atomic test and set to get the lock and test at the same time, right? And when you're done, you better unlock it. Otherwise, you lock everybody else out, right? It's like you lock it, throw away the key, and then everybody gets stuck, right? So that's a protocol. It's an agreement. Everybody better follow. But how can you enforce this? Well, you need to depend on programmers obeying this protocol. There's no other way OS can enforce this, unless it does a timeout or something, right? So anyway, so yes, and to unlock, easy. Just set it to false. No need to check anything. Okay, just set it to false. And so that's how atomic test and set can be used to implement a lock. Right, so you can do something like this, while test and set of lock. So while it's spinning, that means the lock is still true, or it's still locked. When you fall out of that while loop, which means test and set returns false. Yes, you got the lock. You go ahead and enter your critical section. When you're done, please set the lock to false. Unlock it, okay? But it's easy to forget. So that's why there are certain languages with support to help you unlock it in case you forget. Okay? So what would be an example? Okay, my favorite language, Python, does this. So you can do a with statement, and then on entry, you do the lock. And when you drop out of the with statement, it unlocks it automatically. So you can do that. Okay. Same thing with the file as well. You can with open and it adds some file handle, and by the time you drop out of that with statement, it closes it. Okay. So these are things where the language level can provide support to make sure these concepts, these primitives are matched up to help you ensure your protocols are properly followed. Okay, so locking by while test and set of lock, and then unlock simply by setting it to false. So atomic compare and swap is more of a higher level, more complex and more general instruction. You can generalize it to atomic, you can use it to implement atomic test and set as well. But then what it does is you pass more parameters. So that includes the, you might call locking variable itself, and then the expected value and the new value. So what it does is also similar. You save the old value into a temporary, and you do a comparison. Okay. So if the current shared variable, this is more a control variable, is equal to your expected value, then you override that control variable with the new value, but you still return that old value. Okay, so one possible way to use this is certainly you can use this to implement atomic test and set, right? Because you just limit to the Boolean, but then now it's an int, so you can encode more things such as the process ID or owner of log somehow. So that way, it actually captures more information there. Okay, so atomic variables are, you can say, potentially hardware supported, but oftentimes language level support. You may have more limited operations, so increment, assign, but not general calculation. And so this oftentimes could also be implemented in conjunction with this atomic compare and swap. It's not the same as a critical section because, say, for example, if you have single producer, multi-consumer, and you have both consumers trying to grab an item from the queue enqueued by the single producer, well, they both can proceed when the count becomes 1, but then only one of them is supposed to get control. So that means it doesn't quite achieve this mutual exclusion property as a critical section would require, okay, if you just use atomic variables. So this is more limited to single updates of shared data rather than being these control variables on your shared data structures. Okay, and so let's go back to mutex locks. So mutex locks is one where we've seen mechanisms for you to implement locks, but what you want to do is to raise this to programming language level, provide some kind of API so that the programmer can call it instead of inline assembly everywhere. So what you can do is, and this is really the standard terminology, acquire and release. Acquire is to acquire a lock before entering a critical section, and release is to unlock, and both should be atomic. And Boolean variable will be the lock to indicate the state, whether it's locked or unlocked. And usually it's implemented via hardware atomic instructions. Okay, so if you just do this, just using the basic hardware primitive, the problem then, of course, is a lot like polling. Same issue with polling. You just keep spinning on it, it's all spin lock, right? So to make it more efficient, you do want to allow the ability to do context switch. But I mean, that's not always the case. And there's some discussion later as to whether you really want to do this kind of spin lock versus kind of a wait. Okay, let's take a break here.